Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action, a course in groups, rings, and fields. This is the first lecture in the series of lectures on rings, and this lecture motivates why we study rings, what kinds of questions we want to ask about rings and why. We do this in the context of looking at Diophantine equations. When we want to solve Diophantine equations, it's natural to try to have a larger set of integers and be able to do number theory on a bigger set of numbers. So briefly, a ring is a set with two operations. One we call addition, one we call multiplication, and we usually denote it with plus and times. You write parentheses r comma plus comma times to show that you have this set R and it has these two operations. These two operations have to satisfy some basic properties. With addition, we have to have an abelian group. So what does that mean? It means that we have closure. If you take two elements and apply this operation, addition, to them, you get a third element of the set. The addition also have to be associative. So a plus b plus c, the same as a plus b plus c. We also need an additive identity. We need a zero. That's an element that if you add to other things, nothing happens. We also have additive inverses. So for every element a, we have a minus a. And we also have commutativity because it's an abelian group. A plus b equals b plus a for every two elements a and b. So with addition, we have a familiar object. You've got closure, associativity, additive identity, inverses, and commutativity. With multiplication, we have much less. Basically, all we have is closure and associativity. If you take two elements and multiply them, then the result should be in your set R. And also AB times C should be the same as A times BC. We have two operations. They also have to connect to each other, and they do that via distributive laws. A times B plus C should always be A times B plus A times C. And because we haven't said that the multiplication is commutative, we also have B plus C. A should be BA plus CA. This is what a ring is. A ring that has two operations with these very basic properties. Sometimes we also have a multiplicative identity. We denote that multiplicative identity by 1. That's an element that if you multiply by other things, nothing happens. If we have that, then we say that we have a ring with identity. Sometimes a ring with unity or unitary rings or unital rings. All of those mean the same thing. I'm going to call them ring with identity or ring with a 1. Addition has to be commutative, but if multiplication is commutative, then we say that the ring is a commutative ring. If it has an identity and it's commutative, then it becomes a commutative ring with identity, which is the main topic of the lectures that are going to follow. So in a ring, you can add, you can subtract, and you can multiply, but you cannot necessarily divide. A prototypical example would be the set of all integers. You can add two integers, multiply them, subtract them, but you can't divide because 1 divided by 3, for example, is not an integer. Studying rings has a lot in common with the study of groups, and in fact, with the study of other algebraic structures. Groups are sets with just one operation and closure, associativity, identity, and inverses. In groups, you focus on substructures, on subgroups. In rings, you focus on subrings. We look at homomorphisms, maps from rings to rings, ring homomorphisms, just like group homomorphisms were important. And in fact, those subrings that are kernels of homomorphisms are especially important. In groups, the subgroups that were kernels of homomorphisms ended up being the normal subgroups. Ideals is how you study rings, and those are the subrings that can be kernels of homomorphisms. Ideals will allow you to construct quotient rings, just like we did in groups with quotient groups. We have also homomorphism theorems, just like in groups, and a very similar homomorphism diagrams and isomorphism results. However, each algebraic object has its own character. For rings, you have to build your own different intuition. There's different motivating questions. They have different prototypic examples that are helpful in understanding rings. The applications are different and the history is different. They came from different places, which is why they have their own vocabulary. For example, we do not say an abelian ring. That's not a thing to say. We say commutative ring, whereas we say abelian group for a group that's commutative. We say normal subgroup, but we don't say normal subring. We say ideal. The history of rings is associated with Diophantine equations, which is what we want to focus on as a way of motivating why we would want to study rings to begin with. And so rings are not just groups with two operations. If you really want to learn rings, you've got to learn them on their own terms. In fact, even commutative rings are very different than non-commutative rings, and they have very different flavors, different tools, different ways of thinking about them, and different kinds of questions. Here, we mostly are going to deal with commutative rings with identity. And when we say commutative, we mean that the multiplication is commutative. Addition is always commutative. And identity means that not only we have a zero, we also have a 1. And as I have been saying, the study of rings arose in the context of solving Diophantine equations. What's a Diophantine equation? Diophantine equation is a polynomial equation in several variables where we want integer solution. These are very natural things and have been studied for a long time. For example, you might be looking at patterns of integers and you may be wondering, if you take the cube of an integer and the square of another integer and subtract them, will the difference of the cube and the square ever be 2? Does the equation z cubed minus y squared equal 2 have any solutions, have any integer solutions? We're only interested in integer solutions, and that's what makes this Diophantine equation. For example, in this case, if you put z equals 3 cubed becomes 27, and then plus or minus 5 for y, that gives you 25, and then you get 2. And so there are two solutions: z equals 3, y equals 5, z equals 3, y equals minus 5. But are there others? These Diophantine questions are tough. And one very good example of that is what's known as Fermat's last theorem. This says that if n is greater or equal to 2, then x to the n plus y to the n equals z to the n has only trivial solutions. That means that either x has to be 0 and then y and z have to be the same, or y has to be 0 and then x and z have to be the same. If n was 2, this would be x squared plus y squared equals z squared. There are plenty of solutions. 3, 4, 5 is an example, but there would be plenty more. Fermat in the 17th century conjectured that this does not have any non-trivial solutions. Actually, Fermat said that he had a proof, but no one believes that he did. It took some 350 years and work of hundreds of mathematicians to finally prove this. The final touches of this was done by Andrew Wiles in 1995. That's when the proof was completed. But in the meantime, in the 350 years that people worked on this, all kinds of areas of mathematics, including abstract algebra, were developed mainly to attack this problem. This problem, by the way, doesn't have any applications that I know of. The fact that x to the n plus y to the n equals z to the n does not have any solutions doesn't buy you anything. But the effort to solve it actually does, and did. To illustrate why this kind of problem is hard, let's focus on Euler. Euler in the 18th century proved one case of Fermat's last theorem, that x cubed plus y cubed equals z cubed does not have any non-trivial integer solutions. And then he made several conjectures. He conjectured that the sum of 3 fourth powers can't be another fourth power either. And also x to the fifth plus y to the fifth plus z to the fifth plus w to the fifth equals 2 to the fifth also do not have any non-trivial integral solutions. This problem was open for almost as long as Fermat's last theorem, 250 years. But eventually in 1966, Lander and Parkin gave us this example. In fact, their paper is only 5 lines long and 2 sentences and just says this: look, if you add these guys up, this works. And so Euler's conjecture, which on the face of it seems like a harder conjecture maybe, or a different conjecture than Fermat's, but just as valid, ends up being wrong because some haphazard combination of integers messes it up. In fact, this was one of the first instances where a computer was used to do computing and solve a math problem. Since then, solutions to x to the fourth plus y to the fourth plus z to the fourth equals w to the fourth have also been found. And so this conjecture is just completely wrong. And this shows why working with Diophantine equations is tough. The theory that could come up with these random kinds of solutions is pretty tough. Our point is that in trying to understand how to solve Diophantine equations, commutative rings can be helpful. And we will have 3 examples to illustrate this. The first example we'll just solve with elementary number theory. The second 2 we will solve sort of given some other things that we assume along the way. In fact, the third one will have some surprises for us. So the first Diophantine equation that I want to solve is this: is z cubed ever equal to y squared minus 4 if y is odd? If you take the squares of odd integers and subtract from them the cubes of integers, will you ever get 4? That's what the question is. And the answer is no, there are no such solutions. But the real question is then why? Why is that? I mean, you can check for a while and see, well, there aren't going to be small solutions. But then how do you know that there are no solutions even for very large integers y and z? Y is odd, and we want to solve z cubed equals y squared minus 4. We can factor this in y minus 2 times y plus 2. So the first thing I'm going to say, the 2 factors are going to be relatively prime. Why is that? If they're not relatively prime, something has to divide both of them, y minus 2 and y plus 2. And then that thing, whatever it is, will have a prime factorization. So there will be some prime that divides both y minus 2 and y plus 2. If p a prime divides y minus 2 and y plus 2, then it will have to divide their difference. If p is a factor of y plus 2 and a factor of y minus 2, it'll be a factor of their difference, but their difference is 4. And so that means that p got to be 2. So the only prime that can divide y minus 2 and y plus 2 is 2. 2, but these guys are odd because we said that y was odd. If y is odd, y minus 2 and y plus 2 are odd, so 2 can't divide them, so nothing can divide them, and so their greatest common divisor is 1. So what? Again, we have z cubed equals y squared minus 4. We have factored it, and we know that the two factors are relatively prime. Say a prime divides z, and look at its highest power that divides. If p to the alpha divides z, then p to the 3 alpha will divide z cubed. And then that has to divide y minus 2 times y plus 2. But if p is going to divide y minus 2 times y plus 2, it's got to divide one of them. P is a prime. You can't split it up between the two factors. And because their greatest common divisor is 1, it can't divide both of them. So p to 3 alpha actually will have to divide y minus 2 or y plus 2. And then this means that both y minus 2 and y plus 2 have to be cubes, because any prime that divides z, its cube will divide z cubed, and that whole p cubed will have to divide y minus 2 or y plus 2. That means that y minus 2 is a cube and y plus 2 is a cube. If one is a cubed and the other one is b cubed, then we get that b cubed minus a cubed got to be 4. But can the difference of two cubes be 4? If you look at cubes, you will see that that's not the case. The closest that they can be is right at the beginning when we cube 0 and we cube 1 and we cube 2, and the smallest difference is the difference of 1, but then there's 7, and after that the differences get even larger. Because the difference of cubes can't be 4, we get that z cubed can never be y squared minus 4. In solving this Diophantine questions, what kinds of ideas did we use? We used divisibility. This guy divides that. We used primes. We used greatest common divisors. We implicitly use the fundamental theorem for arithmetic, which says that every integer has a unique factorization into primes. We also use facts like if a prime divides a product, then it has to divide one or the other, or both, but not both if the greatest common divisor is 1. We want to be able to use similar arguments on other Diophantine equations. Our second example is very similar to the first example, z cubed equals y squared plus 2. Are there any integer solutions? This looks like the first example, and we want to know if we can resolve it the same way. What happens if y or z are even? If one of them is even, because we want z cubed equals y squared plus 2, then both will have to be even. If z is even, then if you take z and cube it, then it will have a factor of 8. And so when you divide that by 4, you get a remainder of 0. While if y is even, then y squared will be divisible by 4, and so y squared plus 2 will have remainder 2 when divided by 4. And so z cubed can't be the same as y squared plus 2 because they have different remainders when you divide them by 4. That's a contradiction. So neither z nor y can be even, so both have to be odd. We want to solve z cubed equals y squared plus 2 when z and y are odd. We want to solve it the same way we did the other problem. And so we're going to factor, but the factoring is going to be a little bit different now because y squared plus 2 doesn't factor that easily. Well, it does factor, but you need to use complex numbers and square root of 2. Y squared plus 2 factors as y plus square root of 2i times y minus square root of 2i. Is it possible to say that the greatest common divisor of these two guys is 1? They're relatively prime in some sense. And then can we say that if p is a prime that divides z, then p cubed divides z cubed because the factors are relatively prime. The p cubed can't have p squared in one and p in the other one. And then as a result, say that both of these have to be cubes. Can we make those arguments? You have to be suspicious because, first of all, what kind of cubes do we mean? Of course, y plus square root of 2i is not going to be the cube of 5 or 6 or 7 or something like that because these are complex numbers. We don't necessarily mean normal, usual, everyday primes. What we mean is that we want to be focusing on numbers of the form a plus b square root of 2i. A and b are integers, so numbers like 5 plus 2 square root of 2i or 7 minus 4 square root of 2i. Those are the kinds of numbers that are coming up. And we want to think about primes of that form. And we also want to think about divisibility and cubes and so forth of these kinds of numbers. Our question is that, do they behave like integers? Can we even use the same vocabulary for them? Can we talk about primes, divisibility, being relatively prime, being a cube, and so forth about these guys? And if they do, well, then they're not going to be our usual set of integers, but maybe an expanded set of integers. Let's formalize that a little bit. So d is going to be an integer, positive or negative, not divisible by square of a prime. Then we're going to define the set z joined square root of d, which is going to be all the numbers of the form a plus b square root of d, where a and b are integers. And so, for example, if d is minus 2, then we get the numbers that we were looking for. One tool that will be very useful is this norm function. So we're going to define a function n that takes one of these numbers and gives us an actual integer. And it's going to be defined by n of a plus b squared root of d is going to be a squared minus db squared. It's what you get when you take a plus b squared root of d and multiply it by its conjugate, a minus b squared root of d. If you multiply those, you get a squared minus db squared. This will be a very useful function, mainly because if you take two elements alpha beta in z joined square root of d, then norm of alpha beta is going to be norm of alpha times norm of beta. The proof of this pudding is in the eating. You just pick two arbitrary elements alpha and beta in z joined square root of d, find the norm of each, find the product, find the norm of their product, and you'll see that they're the same. It's just a calculation. Back to our problem. Z cubed is y squared plus 2, and z and y are odd, and we want to now carry out our project, the one that we saw in the first example. The first question is that, are the two factors relatively prime? And we're going to claim that they are. We take one of our numbers, alpha, a0 plus b0 times square root of 2i, and we were assuming that it divides both y minus square root of 2i and y plus square root of 2i. What we want to show is that alpha is either 1 or minus 1. That's what we mean by them being relatively prime, is that no other number of their ilk divides both of them. If alpha divides both of them, you've got to divide their difference. That makes sense. And their difference is 2 square root of 2i. And if alpha divides that, then 2 square root of 2i can be factored into alpha times something else. And that something else will have to be one of these kinds of numbers also. Now we use our norm function. If you take 2 square root of 2i equals alpha beta and take the norm of both sides, you should get the same thing. Norm of 2 square root of 2i is 8, and norm of alpha beta is going to be norm of alpha times norm of beta. But these are actual integers. So norm of alpha times norm of beta is 8. And those are just integers that are multiplied. So there's not that many choices for norm of alpha. The norm of alpha is going to be a factor of 8. It's going to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. That's all it could be. But norm of alpha is a0 squared plus 2b0 squared. So for one thing, it can never be negative. So those minuses are irrelevant. It's actually possible to go through and see what choices for a0 and b0 work. And the only ones that work are these alphas. Alpha can be plus or minus 1. That's the thing we wanted to prove that it must be. Or it could be plus or minus 2, or plus or minus square root of 2i, or plus or minus 2 square root of 2i. Remember, alpha is going to divide both y minus square root of 2i and y plus square root of 2i, dividing both of them. And z cubed was a product of these two. So if z cubed is a product of these two, and alpha is a factor of this one, and alpha is a factor of that one, then alpha squared will be a factor of z cubed. Now, in all of these cases, when you multiply alpha with itself, you get a factor of 2. That will tell you that 2 divides z cubed. But z cubed was supposed to be odd, and this is a contradiction. This contradiction proves that there could not have been such an alpha, and therefore the greatest common divisor of y plus square root of 2i and y minus square root of 2i is 1. Can we argue that if you have a highest power of a prime dividing z, then p to the 3a divides z cubed, and so p to the 3a divides either one or the other factor, and as a result, we can conclude that these guys are cubes. Can we do that? Well, the problem here is that we don't know what a prime is. We don't know how these things factor into things and what would be a prime for this new set of numbers. But if we could do that, then y plus square root of 2i is going to be a plus b square root of 2i cubed. If you multiply that out, you get something like this. If these are going to be the same as each other, if y plus square root of 2i is going to be this cube, then y would have to be the real part, a cubed minus 6ab squared, and coefficient of square root of 2i will have to be 1. So 1 will have to be b times 3a squared minus 2b squared. So let's just focus on this second one. Which two integers multiply and give you 1? Either both of those numbers are 1, 1 times 1 is 1, or minus 1 times minus 1 is 1. The only solutions you get from these is b is 1 and a is plus or minus 1. If you put those back in, you will get that y equals plus or minus 5 and z equals 3 are the only integer solutions to z cubed minus y squared equals 2. So we were able to solve this Diophantine equation if we could argue the same way as we argued with integers with these expanded set of integers, these z joined square root of 2i. And if you could talk about primes, divisibility, greatest common divisors, cubes, and so forth, if all of those arguments worked, then we'd solve this and we got what the solution are. So the nagging questions are, does this thing have primes? And what do we mean by prime? Can you uniquely factor as product of primes? And those are the nagging questions that we will have to answer. Now we go to our third question. And this one, if you solve it slightly differently, you can solve it really easily. But I'm going to try to solve it the same way as I solved the other two Diophantine equations. I want to solve z squared equals y squared plus 5. And something surprising happens. We want to solve it just the same way we solved the other ones. Again, just like in the second one, we will first say that if y or z are divisible by 5, then both of them will have to be, because z squared is y squared plus 5. If z is a multiple of 5, the remainder of z squared when divided by 25 will be 0. And if y has a factor of 5, then y squared plus 5, when you divide it by 5, will have remainder 5. And those are not the same. So we can't have y or z divisible by 5. We want to factor this, and this time we factor very similar to the second case, y plus square root of 5 times I times y minus square root of 5 times I. And we want to consider this kinds of numbers. Z joined square root of 5i, numbers of the form a plus b square root of 5i, where a and b are integers. The question is that, how do these guys behave? And the next thing we need to do is to prove that y plus square root of 5i and y minus square root of 5i are relatively prime, just like we did in the first two examples. We also showed that z and y, neither one is divisible by 5. Our claim is that the greatest common divisor of these two factors is 1. But what we mean by that is that no number of their ilk, no number like them, divides both of them. There's no number of the form a plus b square root of 5i that divides both y plus square root of 5i and y minus square root of 5i. And how do we prove that? We assume that alpha, a0 plus b0 square root of 5i, an element of z joined square root of 5i, divides both y plus square root of 5i and y minus square root of 5i, and we want to show that alpha is plus or minus 1. If alpha is a factor of y plus square root of 5i and also a factor of y minus square root of 5i, when you subtract them, alpha will also be a factor of that. But when you subtract those, all you get is 2 times square root of 5i. And so alpha will have to be a factor of that, which means that 2 times square root of 5i will be alpha times something else. And that something else will also be an element of z joined square root of 5i. What do we do with that? We take the norm of both sides. The norm of 2 times square root of 5i is 20. And norm of alpha beta is norm of alpha times norm of beta. But these are now integers, and we have 2 of them that multiplied and gave us 20. So they have to be factors of 20, but they're not any factors of 20. They're of the form a0 squared plus 5b0 squared. For example, n of alpha can't be 2. There's no way you can pick an integer a0 and another integer b0 and make this guy be equal to 2. First of all, you can only make positive integers, and the only things you can make are 1, 4, 5, and 20. And you can go through the other factors of 20, like 2 or 10, and convince yourself that there's no way that you can find 2 integers a0 and b0, so that a0 squared plus 5b0 squared is 10. N of alpha is only 1, 4, 5, or 20. And because, again, alpha is of the form a0 squared plus 5b0 squared, we can actually figure out what the possibilities for alpha are. For example, if n of alpha is 1, the only way that this quantity can be 1 is if b0 is 0 and a0 is plus or minus 1. The only way it can be 4 is if b0 is 0 and a0 is plus or minus 2. N of alpha can be 5 if a0 is 0 and b0 is 1. And then alpha will be square root of 5i. If b0 is minus 1, it'll be minus square root of 5i. So these are the only possibilities for alpha. If it's plus or minus 1, we're happy. But what if it's the other things? If alpha is plus or minus square root of 5i or plus or minus 2 square root of 5i, then we know that alpha was supposed to be a common factor of y plus square root of 5i and y minus square root of 5i. If it's a factor of this one and that one, and z squared is the product of those, then that means that alpha squared will be a factor of z squared. But alpha squared, if you multiply these, it will have a factor of 5, which will mean that 5 divides z squared, but we had said that z is not divisible by 5, so that cannot be. Now, the other possibility is if alpha is plus or minus 2. And if that's the case, then y plus square root of 5i has to have a factor of plus or minus 2, so it'll be plus or minus 2 times something gamma. We can take the norms of both sides again, and we'll get that the norm of y plus square root of 5i is the norm of plus or minus 2 times norm of gamma, and that will tell us that y squared plus 5 is 4 times norm of gamma. And norm of gamma, whatever it is an integer, so 4 divides y squared plus 5. Y squared plus 5 is a multiple of 4, but that's not the case. Why is that not the case? Well, there are 2 cases. Y could be even or odd. If y is even, then y squared will be even plus odd will be odd, and odd is not going to be a multiple of 4. If y is odd, then y is of the form 2k plus 1, 2k plus 1, and 2k plus 1 squared is 4k squared plus 4k plus 1, so y squared plus 5 will be 4k squared plus 4k plus 6. The 4k squared plus 4k have a factor of 4, but 6 doesn't. And so y squared plus 5 is not a multiple of 4, and that's a contradiction. So the only possibility for alpha is plus or minus 1, and we have proved that the greatest common divisor of these two, y plus square root of 5i and y minus square root of 5i, is 1. This is what we have. Can we argue that if a prime divides z, then p squared will have to divide z squared, and then p squared will have to divide one or the other of y plus square root of 5i and y minus square root of 5i, and therefore these should be squares. If that's the case, then y plus square root of 5i should be a plus b square root of 5i squared. If we square that, we get a squared minus 5b squared plus 2ab squared 5i. That would mean that y is a squared minus 5b squared, and 1 has to be 2ab, but you can't have 2ab be 1 ever. So that would tell us that this has no integer solutions, and we seem to have solved the problem just like we did before. That's reassuring, except for the fact that it's wrong. It's wrong because there are solutions. Z could be plus or minus 3, and y could be plus or minus 2. And if you put those, you get 9 equals 4 plus 5. There are solutions. How did we miss that? What went wrong in our system? The key fact that went wrong this time is that in this new world of z joined square root of 5i, we have 3 times 3 is 9, but that 9 is also 2 plus square root of 5i times 2 minus square root of 5i. And 3 is not a factor of either one of those. Neither one of these can be further factors. So 3 divides 9. So 3 divides 2 plus square root of 5i times 2 minus square root of 5i, but it doesn't divide either one of them. And that's not something that happens in our world of integers. So our argument for arguing that each one of those factors has to be squared is not going to work, because we have these sort of double factorizations. When a number like 9 can be factored in 2 different ways, the problem is that 9 has 2 different factorization. And the fundamental theorem does not hold. That's a problem. That third solution was just wrong. We just can't do that. So now that casts doubt on our second solution. So what about that? We've used that same argument and we found these solutions. It's easy to check that there are solutions, but maybe there are others that we missed. The fact is that that proof is actually okay. And the reason is that z joined square root of 2i does have unique factorization. There is a fundamental theorem for arithmetic for that set of numbers, whereas there isn't one for z joined square root of 5i. Something is fundamentally different between z joined square root of 2i and z joined square root of 5i. And that is surprising because they just look very much the same. And that's what we need to study in ring theory. In ring theory, we like to study this z joined square root of 5i and z joined square root of 2i. Both of those are rings. They're places where you can add, you can multiply, you can subtract, but you can't necessarily divide. And we want to study them the way we would do number theory. So the kinds of questions we want to ask is that, can we define divisibility in primes for arbitrary rings? Can we do that? And here I mainly mean commutative rings with identity. For which rings do we have a fundamental theorem of arithmetic? Like we have primes, and we can say that we have a unique factorization. And other questions, for example, an ordinary prime, how do we define it? We say that an integer is prime if there's no way to factor it, if it doesn't have any factors other than itself and 1. But also for prime p, the property that we actually used was that if p divides a product, then it divides one or the other. For which rings are these two things the same? Being a prime is the same as having this other property. That's a guiding question for us as we go through ring theory. Another question is, for which commutative rings do we have a division algorithm? For integers, when we take 2 integers, you can't divide them, but we have the division algorithm, which says that you can divide and get a quotient and a remainder. You might not be able to fully divide, but you can get a quotient and a remainder. And then that remainder is smaller than the thing you divided by. That is very useful. In particular, you can use that to prove the fundamental theorem for arithmetic. We want to know, when do we have this division algorithm in what kind of rings? Another question would be that the integers are inside a field, the rational numbers. We think that we can divide integers. It's just that sometimes we don't get integers. But it's helpful to know that we're sitting inside a bigger field. That gives us a better perspective. Is that possible for other kinds of commutative rings? Can we construct a bigger field that contains them? So these are the guiding questions that we will answer in our ring theory lectures. This is the end of this lecture. Like this video if you like it, and subscribe to my channel if you like to be subjected to more undergraduate math videos, and keep hydrated at all times. See you at the next lecture.